dissolve and they do not settle down. Another thing they don't do is also scatter light. What that means is if light passes through, it'll keep passing through. If they scatter light, that means that it'll be cloudy because light's not passing through. Okay? Colloids are medium-sized particles dissolved in it. They do not scatter light, but like smoke. That could be considered as smoke considered as a colloid because light does not pass through, but they don't generally settle. Right? Whereas suspensions settle, okay, and they do not pass through. They are large particles. Do we know of any suspensions that we can pass? For example, blood is a suspension. Okay? If we leave it long enough, the cells will sediment down. What's that stays? If you've ever seen a picture of blood, they'll have red at the bottom. Sometimes you may miss it. There's a little white and then a yellowy part of the blood plasma, right? So in the blood plasma are cells formed. The elements are really called in suspension. As long as they dissolve, it's a suspension. So they are large particles, they do not scatter, they scatter light and they do settle down. So either they will settle down. Okay? And then we talked about what makes solutions, solvent and solutes. Solvents are what is dissolving agent. What one dissolves in the other, whatever it's being dissolved in is the solvent. What's being dissolved is the solute. Sometimes they talk about smaller amount solute. The one that's in the larger amount is the solvent. Okay? What's the universal solvent? Consider the universal solvent. Water. Water dissolves a lot of things, right? We can put salt into water, it will dissolve. We put sugar into water, dissolves. So those of you who are coffee connoisseurs know what I'm going to say next. If we put coffee granules into water, instant coffee, that dissolves as well, right? So that will be the solute. Okay? So solute will dissolve in solvent to make a solution. So let's talk about these two terms, hydrophilic and hydrophobic. What does phobia mean? Afraid, fear of, right? So hydrophobic means they do not like water. They do not dissolve in water. While hydrophilic means they dissolve in water. Okay? So next I'm going to talk about that polar and non-polar. Water, is that polar or non-polar? Polar. So one thing you want to remember is like dissolves in like. Okay? So if it's another polar molecule, will it dissolve in water then? It will. Ions also will dissolve in water because they're also charged. They'll dissolve nicely in water. Non-polar will not. Even if you didn't know, what is our guess oil is?
Non-polar.
Non-polar. Do they dissolve in water? No. By definition, and it's true, it's only light that dissolves in light. So here, if you look at it, solutions will form if solute and solvent are the same. So if it's polar solvent, we need polar solute. If it's non-polar, they will dissolve only non-polar solute. So it won't dissolve polar solute and vice versa. Okay. Here, like water, we're trying to dissolve oil in, it will not dissolve. If we try to dissolve water in oil, that doesn't dissolve either. Okay. If you are into cosmetics, they're going to talk about how they will put some stabilizers which will help things dissolve in most of the creams and so on, they're oil based or water based. Right? They have to kind of mix them up and they'll add in so it does mix up. By itself, it will not dissolve in the other. So, what makes a molecule hydrophilic? Yeah, polar molecules will dissolve in it. Same thing with ions too. They don't have to be covalent ions. Salt, does it dissolve? Yes. It is an ionic molecule. It will dissolve. Lipid molecules are hydrophobic because they are non-polar. And what does hydrophobic mean? It is fearful of water, it does not dissolve in. Okay, so I didn't put light, dissolve. Polar solvents and polar solutes will mix, not the other way around. While non-polar solvents, we do have non-polar solutes. What is solvent again? And what's solute? Yeah, dissolving the solute, or it dissolves in universal. Good. Okay, so here is some. Oh, here's the. I wanted to show this earlier. Solution, small particles that do not settle and do not. Here's talks about separation, but also do not scatter light. Colloid, larger or medium-sized molecules that do not settle, but they do scatter light. Okay. While suspensions, very large particles, cells in our blood, for example, they will settle and they will scatter light. That's our blood, whole blood. Here it's separated out. The white blood cells at the bottom. This image is not the fluffy coat, it's a molecular coat. The white blood cells, platelets, but the yellowy orange here is the plasma. That's a suspension. Next, we're going to talk about some molecules. So we're going to talk about inorganic compounds and then organic. How we distinguish them is the presence or the absence of two elements. If we have them both, they're called organic. If we do not have them both, we can have one, but if not the other, then they are considered inorganic. So here is this. So it is carbon and hydrogen. So is carbon dioxide organic or inorganic? Organic molecules have got carbon and hydrogen. I don't have it up here. What about glucose? What was the molecular formula for glucose? C6H12O6. Is that organic or inorganic? Organic. Carbon and hydrogen. Okay. So here we'll talk about carbon dioxide. We'll talk more in terms of chapter 4. And in our respiratory system, we'll talk about how we get rid of it. Right? So whenever we break down glucose, we'll break it down to carbon dioxide and water and ATP. That's why we break down glucose. Oxygen is also considered inorganic, right? Because it doesn't have carbon or hydrogen. We're going to talk a little bit more about water. Okay, so water is organic or inorganic? Inorganic. So just in case you didn't know, how much of our body is water? Yeah, it's quite large, between 60 and 80% of our body is water. It depends on our age, depends on our size, and so forth, right? But it's about, average would be about 70% of our body is made up of water. Okay? So about 2/3 of our total body weight is water. So some properties, it is a universal solvent, right? So anything that's polar or ions will dissolve in water, which is a polar molecule. So high heat capacity and heat vaporization, that's because of those hydrogen bonds. So what this means, the first one, high heat capacity, how much heat can it absorb before the temperature of water changes. Okay? If you've watched a kettle, maybe you have noticed, maybe you haven't, we turn on a kettle. The reason why it takes a long time to boil, and if you watch your electrical meter too, you're going to see that spinning, okay? Because it's using a lot of electricity to boil that water. Because water takes up a lot of energy before the temperature rises. That's heat capacity. And then what do we think about vaporization? It goes to becoming vapor, right? So normally when we boil water, we want it to reach that point and then we stop it so that it's still consuming as liquid water, but not vapor. So think about when we sweat. Why do we sweat? How does it cool off? Yeah, why?
The water absorbing the heat.
Yeah, it's going to take the heat from our body. Put a drop of water, blow on it, and take note of what you feel on that spot. Okay, when that water leaves, that spot feels cool because it's taken the energy, the heat away from our body, which is why we use it to cool us down. It takes the heat away from our body because it has high heat capacity and high heat vaporization. Okay? Then we also talk about surface tension. That's this at the surface, the water molecules are bonded together, it's kind of forming a nice barrier too. Okay? For some properties of the water. Next one we're going to talk about is acids and bases. So, definition of acids is twofold. One is this nice one. It dissociates into H plus ions. Okay? When you talk about acids and bases, how do we measure acids and bases? pH level. How is the pH written? The word pH, if you will.
So lowercase b, capital.
Yeah. Have you wondered why?
Is it like part per million or hydrogen or something like that?
It is. So the emphasis here I wanted to get to is that hydrogen. Right? It is a measure of hydrogen ions. Basically, that's what pH is. Okay, it's a measure of hydrogen ions. We base it by how much hydrogen ions it has. If it has a lot, that's an acid. Where is it on the pH scale, by the way? Low or neutral or high? 0 to 6, because what's considered neutral pH? 7, right? So below 6, it actually has more H plus ions. It's a negative logarithm to get more than for our course, but understand what we need to recognize is the lower the number, the more H plus ions it has. Okay? The higher the H plus ions it has. We'll talk a little bit about that. Another thing is acids are also defined as a proton donor. Why? Go back to our periodic table. Okay. What made up hydrogen atoms? One proton. How many neutrons? In the commonest one. 0. How many electrons? How did H plus ion come to be? What happened to the hydrogen atom? Loses electrons. So when this loses electrons, what's left? So hence it's also called a proton donor. Okay, so it will give off H plus ions. While bases, on the opposite side, alkaline bases, they have two explanations as well. They will dissociate into OH minus ions, or kind of opposite of acids, they are proton donors, or they will remove H plus ions. Okay? They will remove H plus ions, or they will take away. When we get to that lab, I think it's either next week or week after. We have an acid-base lab. I'll ask us for definitions of acids. That's what I'm looking for. They dissociate H plus ions, they are proton donors. Bases, they'll dissociate with OH minus ions, they will be proton acceptors, or they will remove H plus ions. Okay? Why are they called proton donors? It's basically H plus ion, basically. Here's our pH scale. So it's basically what's a pH scale. Again, that level. Go over it one more time. I'll say it's a measure of H plus ion. That's enough for our course. That's what we need to realize. Okay. When you go to chemistry, they're going to talk about how to calculate it, how to take our scale. We need to know as a measure of pH, H plus ions, and then what's neutral. What happens when pH ions is high? What happens with low? As well, higher than and lower than. Right? So, for example, neutral is 7. Here, really, H plus ions and OH minus ions are equal to each other. Okay? While acids will have a lower pH, bases will have a higher pH. Anything above 7 is a base, anything below 7 is an acid. 7 is
Okay.
Okay. But please remember, higher the H plus ion concentration, lower the pH. So something that is pH of 1 is a lot more acidic than something that's pH 5. Okay? Stomach acid is pretty much 1, maybe 2, sometimes depending on what you're consumed. Okay, but it's hydrochloric acid in our stomach. Coffee is acid. Okay. Wine, beer, acidic. Anything that tastes sour, citrus fruits, they generally have acid in them. Okay. Urine can vary. Well, blood, we'll talk about it. It's actually slightly on the base scale. It's not neutral. It's not 7, but it's about 7.4, 7.35, 7.4. So pH of 7 is neutral, less than 7, that sign tells us less than. 2 dots goes one side, less than 7 in acid, greater than 7, 2 is 1, 2 greater on this side is base or alcohol. Okay. Higher the H plus ion concentration, what will happen to the pH? Lower the pH. Called pH because it is measuring H plus. Any questions? The blood is the pH of blood. We'll talk more about using. So in terms of how do we regulate? What is homeostasis, by the way? Regulation to maintain some sort of equilibrium, right? pH is the same. We don't want it to go too far up. Temperature, we don't want it to go too far up. A little bit low, it's fine. You tolerate. A little bit high, you tolerate. Not too high. Okay? So generally, we have things that are trying to prevent large changes. Okay. Let's introduce buffers. So buffers is something that prevents large changes in pH. They won't necessarily stop it, they don't necessarily neutralize it, but they'll try and reduce the change. Okay? We do have a lab on this to maybe elaborate about what makes an acid a strong acid versus a weak acid. I'll do that in the lab. A little bit of lab. So what we need to take away from here is it is a system that has two parts. It prevents large changes in pH, right? So if we have acid, if I add hydrochloric acid, what will it do to the pH? Hydrochloric acid lowers it down. If I add NaOH, that's sodium hydroxide. If you didn't guess what it does, so sodium hydroxide, what's that going to do is it can form from and can dissociate. Oh, by the way, if it means dissociate, I don't know if you understood that, it means to separate into the ions. HCl, hydrochloric acid, will dissociate to H plus and Cl. That's the H plus that we're considering here, and basis is the OH minus. Okay. So we'll talk more about how they do that. Just recognize that the function of them is to prevent large changes in pH. While saturation, if I said the word saturation, what comes to our mind? A lot of it, yeah, right? So for example, if I have a glass, I added some salt, dissolved, fine. And keep adding, there will be a certain time where no more salt will be dissolved, actually just salt at the bottom. Okay? It's reached its limit, if you will. Saturation is reached its limit. Okay? Here too, a buffer, if it is reached its limit, we say it's saturated. We'll test this out in lab. If I'm not mistaken, it's next week. No, it's the third or the fourth lab. We'll test it out, okay? Because it will not function. What do you think will happen to pH then? As a function of buffer? Yeah, it kind of will not change the pH. Too much here will start changing once it reaches saturation. We actually have two buffers. One will be a good buffer, one will be not. We'll see how they do. If it's a good buffer, it maintains the pH. It can change slightly, but not. And we'll talk about what's a strong acid basis which will create it. So saturation is when the buffer has reached capacity, it's not able to do its task, it's not able to prevent large changes. We'll talk more about this one. So next we're going to talk a little bit about some of the organic molecules. So what's the definition of an organic molecule?
Contains carbon and
Contains
hydrogen.
carbon and hydrogen. We're going to look at 4 groups. They put this in your textbook as a separate one. A lot of books put it together with nucleic acids. We'll talk about that. Okay? So carbohydrates. What is to hydrate? That says I'm dehydrated. You have lost water, right? So carbohydrates basically tells us what elements it's found in. Okay? It's going to be carbon, hydrogen, and water. Okay? All of them will have carbon and hydrogen. Some have different amounts of it, and then some have additional elements too. So first one we're going to look at is carbohydrates. They contain carbon, hydrogen, and oxygen. The rule is we have, for every oxygen, we'll have 2 carbons, right? So we looked at glucose. What was the molecular formula for glucose? Yeah, so we have 6 oxygens. For each oxygen, we have 2 hydrogens. So we have 12 hydrogens. Okay? And it's usually our energy source of our body. So we'll talk about mono. What's mono mean? One. Monosaccharide simply translates to one sugar. Okay? So then what is this one sugar? It's one unit. Okay? Glucose is a monosaccharide. Okay? While starch, it's going to be made of multiple glucose molecules. This why we consume food with starch, what happens to our glucose levels in blood? It will go up. Okay? And which hormone will try and reduce that? Insulin. Our body normally releases it. You think about diabetic patients, they have either they do not produce enough insulin, or their insulin that they produce is not efficient. It's not their body's resistance to it. So here are some other examples: glucose, fructose, and galactose. Ribose by itself, it doesn't exist, generally with something like RNA is ribonucleic acid, as a ribose sugar. While what is disaccharide? Di means two, so two sugars. We'll look at 3 disaccharides. Here memorization. Sucrose, lactose, and then maltose. These are all very common. They're all disaccharides. Where do we come across sucrose? Anybody know where sucrose is found in our daily life, if you will? That's our table sugar. That's actually sucrose, not glucose. Okay? Where is that one found? Milk, right? Some people are lactose intolerant and not able to break down lactose. While maltose, malt, beer, whiskey, yes, as well as in barley, that's where it came from. Okay? These are all disaccharides. Okay? They're basically a combination of monosaccharides. All of them have glucose. At least one glucose. Okay? Sucrose is glucose plus fructose. It will be R helps. While lactose is glucose plus galactose. While maltose, I can't give you a hint to help them, they're just 2 glucose molecules. So, lactase enzyme, we learned that it's in our intestines, it's in the brush water, that will break down lactose to glucose and galactose. Sucrase enzyme, we have that too, will break down sucrose to glucose and fructose. Talk about maltase enzyme, that will break down maltose into 2 glucose. So those are disaccharides. Okay? Then we have others that are many of these monosaccharides together. We call them polysaccharides. 2 are very important. One is starch. Is starch found in animals? That's only found in plants. We get them from potatoes. I know we get them from pasta, but where did they come from? It was from flour, which was from plants. Same thing with bread too. It's from the flour that came from plants. It has the starch in it. Okay? So that's storage form in plants. While what is our storage form? What happens to excess glucose first? Now, later on, if you tell me fats, I'm going to say that's later on. What happens to excess glucose in us first? What does insulin promote? One thing it's going to tell cells to absorb as well as convert it to
Energy.
You can break, the insulin itself does not break it down. You're going to store it to, it's also a G word, not heard, it's glycogen. Glucagon is a hormone, top bladder. So in us, it's glycogen. So first we'll store it as glucose. We have excess will convert it to glycogen. If we have more glucose, then we start turning into fat. Does anyone know what type of fat it is? So we can store this when we need it. We'll break that down. So first we'll consume glucose in our body, whatever storage we have. Then we'll break down glycogen. Then only we'll break down triglycerides, but at the same time we'll also break down proteins at this stage. Which is why when we work out, when we go to that level, we need to make sure we're consuming proteins and amino acids with it. Store it, it's first glucose, then glycogen, then triglycerides. That's how it's so lipids, they are also carbon, hydrogen, and oxygen. But here we don't have as much oxygen. For example, we don't need to know names of them, but we may have a molecule such as that. That would be a lipid rather than a carbohydrate. I'll draw something similar. Which one of these two is a carbohydrate? Which one of these is probably not? It's not. Which one's a carbohydrate? This one, because it has been 2 is to 1. Okay, this one, 22 and then it's going to be 2 oxygens. That's a lipid. A lot more hydrogens in compared to the oxygens. But carbohydrates is only about double. So why do we store it as that? Why not keep it as glucose, as glycogen? The reason is here. Okay, each gram of fat stores double the amount of energy as a gram of carbohydrates, as even a gram of proteins. Okay? It's about 9 kilocalories per gram of fat that we can get out, compared to about 4 for carbohydrates, about 3.8 for proteins. Okay? So a lot more fat, a lot more energy can be stored in a smaller weight. This was because of the way we used to live. We were nomadic, we used to hunt, we used to eat, and then we would have to go to another place. So in part, it was beneficial for us to store it, yes. For us, it has been a problem sometimes when we're trying to get through it. Right? We want to get rid of fat. We work through first the glucose, then the glycogen, then we tap into lipids. We also remember tapping into breaking down some proteins at the same time. Okay? So lipids store about twice the energy per gram, twice the energy as carbohydrates and as proteins. Okay? Why are lipids insoluble in water? Why are they hydrophobic? I heard hydrophobic. Yes, they're hydrophobic. Why? They're non-polar. And polar dissolves in polar. Water is polar. Liquid is unless there's a higher temperature. Let's talk about lipids and okay, let's finish with it. So we have, in terms of lipids, there's 4 types, if you will. One is technically not what we talk about. So fatty acids, then we have triglycerides, we have steroids, and we have phospholipids. So who had lab, where's phospholipids produced in our cell? What organelle produces phospholipids? Which membrane? Oh, it's found there, but what produces it in our cell? One of the ERs. One produces one, the other one produces all others. So rough ER will produce the phospholipids, the others are going to be biased. Okay, so while you might hear lipoproteins when they talk about cholesterol and so on, but they're really talking about lipids with proteins together. Okay? We can measure that in our blood. One I do want to talk about is this one, high density lipoprotein and a low density. Please remember that the high density one is considered the good cholesterol, while the low density one is considered the bad cholesterol, which can form a part of atherosclerosis. It doesn't start the process, but that will continue the process of atherosclerosis. Okay? When we exercise, we'll convert some of this bad cholesterol to good cholesterol. Okay. So let's talk about fatty acids. The fact we talk about, okay. Just note they have a group called the carboxyl group. Okay? This carboxyl group is COOH. The fact that it's an acid, what do you think what it gives off? Dissociates into hydrogen ion. So this hydrogen will come off. That's why they're called acid. Fatty acid, amino acid. These organic acids have this group, carboxyl. Okay? Any of you must know it. Look from this way. Look back once. But let's talk about the saturated fatty acids, which we do hear about, versus unsaturated fatty acids. The saturated here, again, what does the word saturated mean? Reached its maximum. Here it's talking about maximum number of hydrogen atoms. Okay? This means these carbon is single bonded. Remember, carbon dioxide has double bond. This has a double bond. For example, I'm just going to draw a very small molecule. Is this stable? Looks good, right? Hydrogen has one bond each, no problem. How many bonds does this carbon have? Total bonds? 4. 1, 2, 3, and 4. Is that stable? Yeah. This carbon atom? 1, 2, 3, and 4. That's stable. Okay? This would be considered, if it was part of the molecule, I'm only drawing a small one, this would be considered unsaturated. Because what would look like saturated if it had the maximum number of Is this stable? Let's make sure we are okay with that. Each hydrogen has one bond each. What about the carbons? Stable, not stable? How many bonds does carbon need to make? How many electrons does it have at the outermost shell? 4. How many bonds does it need to make? 4 bonds. Right? That shows. Oh, by the way, what does this show again? Double bond, right? So 2 electrons each of each. Okay? So that's what the saturated versus unsaturated talking about. Can we add more hydrogens into this molecule? If we can, it's not saturated. It's considered unsaturated. We have maximum number, it's considered maximum number is considered saturated. They didn't show the hydrogens, but basically it depends on the carbon. Because how many bonds can hydrogen form? Just 1. Doesn't matter, right? While carbon can form 4 bonds, right? Unsaturated means there is a double bond in there. Again, they haven't shown the hydrogens, but we could potentially add 2 more by breaking that double to a single bond, right? Here, I converted this 2, when this double bond between the 2 hydrogens to single, we needed 2 more hydrogens to fill up to sterilize this one. Okay? That's the difference between saturated versus unsaturated. Saturated means that maximum number of hydrogen atoms. This only exists if we have single bonds between carbon. If we have double bonds between carbon, they're considered unsaturated because we potentially add hydrogen atoms to this molecule. Okay, that's another one. Unsaturated versus saturated fatty acids. 2 minutes. 3 minutes, I guess, with triglycerides, phospholipids, and steroids. So triglycerides, that's our storage form of fat. That's what we will convert extra glucose into. Okay? So energy reserve. We can also use it to insulate our body, right? In terms of how many body actually insulates organs too. So in terms of our body, in our skin, one of the layers is called the it's not technically part of our skin, it's below our skin, it's called the hypodermis, which has a lot of fat. Okay? If you look especially at animals that live outside, they do fluctuate, this fat content fluctuates during the year. Okay? During winter time, they'll start storing more fat there. Yes, it's got energy, but also insulates them. Okay? It also forms cushioning because it was absorbed. When we get to the tissues lab, we'll look at kidney, we'll look at the fat around the kidney. Okay? Because it cushions the kidney as well, it absorbs some shock. So, what does tri mean? 3. Here it's not the glycerol part. What is 3 is 3 fatty acids. Okay, so it's 1 glycerol and 3 fatty acids that we do. Because when we talk about phospholipids, there is some similarity, 1 difference. Okay, so with 1 glycerol and 3 fatty acids. Oh, by the way, in terms of saturated fats versus unsaturated fats, saturated fats are solid at room temperature, while unsaturated fats are liquid at room temperature. So what is peanut oil going to be? Unsaturated. What's the fat from, say, meat fat? Saturated fat. Solids at room temperature, saturated fats, or unsaturated are liquid. Phospholipids. So what the phospho part is, we have a phosphate. Oh, by the way, going back here, it is non-polar. What does that mean then? Will it dissolve in water?
No.
No, it will not. While phospholipid is very interesting, very important. Okay? What is it made up of first of all? 1 phosphate group, 1 glycerol, and 2 fatty acids. What's triglycerides made up of? Yeah, 1 glycerol and 3 fatty acids, right? So here, instead of 1 fatty acid, we have a phosphate. Okay? That changes the structure, the integrity of this molecule. It makes this molecule water soluble at one end, that's the phosphate end, and then not water soluble at the other. Which one would be hydrophobic? The fatty acid part is hydrophobic, while the phosphate part is actually hydrophilic. It will like water. How much of our body is water? 2/3, about 70% is water. This actually will form our plasma membrane. We'll talk about this in Monday. It actually will form the barrier. The plasma membrane, the cell membranes are barriers. Will it form it by 1 phospholipid? No, because why not? Why would that not be a good model? We have water. Do we have water inside our cells? Do we have water outside of our cells? Yeah, so we want water-loving sides to face the water, right? So we have phospholipids facing both sides. One last thing, so we'll talk about that again. And the last thing is about steroids. They are basically ring structures. Okay, they are made in our liver. And what are they used for? 2 things. They have become part of our membrane, and then steroid hormones uses steroids that are built from steroids, right? Have we heard of any steroid hormones? Testosterone, estrogen, progesterone, they're all steroid hormones. Okay? We'll talk about bile salts. Where are bile salts found, by the way? They are stored in, they're found in bile. We'll talk about the cell membrane in our chapter 3. We'll talk about how phospholipids is made, but we also have steroids. Questions? Alright, we're all a little bit behind. I needed to spend that time for the atoms of this. Have a wonderful day. See you Monday.
Really? Yeah. And the textbook.